So this is, I believe, the last chapter in this section. So we'll have a test on this section later this month.
I thought you were blowing your nose.
Nope.
He's growling. You just
So this one is on probability models, and we're going to look at something called Bernoulli trials.
Bernoulli?
Bernoulli, yep,
Sounds like a type of noodle.
it does sort of. I think partly because it's Italian.
He sounds old.
Well, he's dead, so. um, So and you'll find on the AP exam they never call them Bernoulli trials.
What do they call them?
There are two types that we're going to look at, and they call them one of those two types.
Oh, okay.
Either a geometric or a binomial model.
They got lame.
Pardon?
So they got lame with it. The names. Like they should just kept Bernoulli. Sounds cooler.
They're not giving him the credit.
I suppose.
That's so cool.
So in order to have Bernoulli trials, you have to have one of two possible outcomes. One which is called a success, the other which is called a failure. Now, I will say with that, sometimes the success is the bad thing, right? Like later on when we're doing things where you're looking at, how many people died of cancer, that could be the success,
Success.
okay? It has nothing to do with an intrinsic idea of this is good and this is bad. It just has to do with this is what we're looking for and this is not what we're looking for, okay? Now, in advance, the probability of success, which is denoted P, is the same on every trial. The probability of failure is denoted Q, and it's always 1 minus P. And you'll see this on the AP exam on the formula page. They don't use Q. They just always use 1 minus P. Okay, so that's one less letter. I use Q, but it doesn't really make any difference. Either is just fine. Thank you. You're welcome. And the third thing, the trials have to either be independent or, if they're not fully independent of one another, we have to use a sample that's less than 10% of the population. And part of the reason for that is that if you were to sample more than 10% of a population, the individual samples start interfering with one another. And you'll actually find this restriction throughout the next section. It just keeps coming up over and over again. And what they'll eventually tell you is that if you have a sample that's more than 10% of the population, you have to use a different set of formulas entirely, and those are beyond the scope of this course. Okay? But it is a requirement that you look at for a lot of these. So first one is the geometric probability. And I want you to write something on this. Geometric probability, your book called it this, and I really like it. It's called waiting for success.
What if it never gets there?
Still waiting.
So this would be like, for example, if you've ever played a game where you have a dice and you have to get a particular roll in order for something to happen. Like at the end of the game, you have to go out exactly. And so you sit there over and over again trying to roll a 5.
Like sorry.
Yes.
What's the bubble game?
After there.
Sorry.
That's trouble.
Oh.
Bubble.
That's trouble with capital T, and that rhymes with P, and that stands
Yes,
for
for
pool.
pool. That's
Yes,
Hugh
pool.
Jackman.
Pardon?
Hugh Jackman.
I watched that
Oh, I bet he's great on that.
He's in it right now in New York.
Oh, that's right. My friend Michael told me that.
Michael.
I have a friend who is an actor in New York.
What?
That's a
Go
flex.
off. Is he at Broadway?
He has not been on Broadway, but
He's getting there.
he was the main character in a national touring company.
Whoa.
Yeah.
That's kind of cool. Okay, Michael.
Pardon?
For what? In what?
Bullets Over Broadway.
Ooh.
Anyway, so any of those games where you're waiting for, you have to keep trying it over and over and over again until you roll that particular roll, okay, or pull the particular card in the case of Sorry.
Like the lottery?
Pardon?
I said like the lottery.
No, because with the lottery, the numbers are always changing. Okay, so if P is the probability of success, then Q equals 1 minus P is the probability of failure.
Bars.
Okay.
There's only two possibilities. Capital X is the number of trials until the first success. Okay, so the probability that capital X, the number of trials until the first success, is equal to little x, which is the number we're going to try and find, is equal to Q raised to the x minus 1 times P. You're like, where does that come from? Well, think about it for just a second. If it takes you 4 tries to make it, right? How many failures did you have?
3.
And how many successes?
1.
So the 4 minus 1 would be 3 failures and 1 success. Okay? Now, the expected value, in other words, how many times you're going to have to do this until you can expect a success, is given by this formula. E of capital X is equal to, what is that?
Mu.
Mu. That's the mean.
Is it mu or mu? I don't know.
It's mu. It's not moo. It's not a cow.
Oh.
It's mu.
To be fair, that could be sounded out like mu too.
No, it
So,
can't.
Keep going. Okay, yeah, you're right. Yeah.
Equals 1 over P. Okay? So if your probability of success is 0.2, be 1 over 0.2, which would be 5. Okay? And then the standard deviation, and this is one where honestly it doesn't get used very much. I didn't notice it a ton in the homework, and I've noticed it not at all on AP problems. Now, haven't worked all the AP problems ever, but just never noticed this one very much.
Did you finish learning your statistics?
I've learned through chapter 21.
How many are there? We're in chapter 6.
25, 26, something like that.
Wow. Very nice.
So I've got 5 more chapters to learn. So the standard deviation in the number of trials until the first success is given by, what is this?
Sigma.
Sigma.
Nice, Kelly.
So lowercase sigma.
Like Greek.
It is.
That was Greek.
Which is when you find as you go further up in levels of math, they start using Greek letters more and more, which is where the phrase, it's Greek to me, came from.
Ah.
Oh.
Wait, a little fun history tidbit.
Language.
Pardon? Lily,
What?
what?
I don't know, some snarky comment. Keep
Okay. A snarky comment? No! Say it's not true. All right. So let's look at an example problem. So, and this is an actual fact, about 8% of men have some form of color blindness.
That's you.
That would be me. Okay? So, first of all, can we apply a geometric probability model to selecting random men and checking for color blindness?
I bet
If
we
we
can.
pick Mr. Davis,
Actually, I have no idea.
Right? So, look at the 3 things that we have to have.
Yeah.
Success, failure, Q.
First, there are 2 possibilities.
colorblind or not colorblind?
Success. or
Indeed. So, does the probability of success change as you go from one person to another?
No.
No. P is always 0.08, and then Q is equal to 1 minus 0.08, or 0.92, for each individual. Now, the trials aren't truly independent because as you select men out from the group, you have less left, correct? You have changed your sample space. Well, that happens a lot, but as long as we pick less than 10%, they shouldn't interfere with one another.
Like less than 10% of the men in the world.
Yeah.
What happens if you pick more than 10%?
Then you have to use a different formula,
Oh,
and I don't know those formulas.
but why does it change the amount?
Okay, so basically what happens is this. So imagine that you are one of the ones that they use as a thing with cereal and it's got some toy surprise that you want in it, right? They make millions of those. So when you get one that doesn't have a toy in it, then the probability that the next one has a toy in it is slightly altered by that one, but not very much. What happens is when you get to more than 10%, it gets to where it actually starts to affect it.
That makes sense.
Okay?
Why
So,
is that true for colorblind men, though?
pardon?
I said, why is that true for colorblind men, though?
Well, okay. So let's assume that there are only 1,000 men in the world, just to make this simple,
Okay.
right? Once you've picked out 200 men, for example, you have effectively changed your sample space now. You only have 800 left to choose from. And depending on how many you picked out that were colorblind and how many you picked out that were not colorblind, you're going to change the probability of another one being colorblind.
Is 10% like a general rule for everything?
For an awful lot of things, yeah. The 10% rule gets applied, like I said, all throughout this next, after this chapter, the next 5 chapters, it's always applied.
Mr. Davis hasn't gotten to the part where it doesn't apply to
Oh, got
Yeah.
He's still on 20.
I think it's going to apply to things beyond that, but
it.
So we will use a sample of less than 10% of all men.
Like 9.9% or like 8%?
Doesn't matter as long as it's less than 10%.
Interesting.
So the answer is yes. All right, so now we're going to randomly pick 8 men, way less than 10% of all men.
You're a man.
I choose you.
Thank you. What is the probability that the 8th man would be the first one that is colorblind?
Oh.
Probably pretty,
So the probability
I don't know.
that capital X is equal to 8 is going to be Q, which is 0.92 to the 7th power times 0.08.
Oh, this is making a lot more sense now.
So our first 7, we want those all to be failures, and we want our last one to be a success. Ian, you got a number for us?
0.04462777281.
We'll usually cut it off after the thousandths place.
Where's the fun in that?
It's not accurate.
I have a
It's
question.
It's accurate
You
enough.
can't do that.
Is it,
It's statistics.
Yeah, go back,
Accurate
go
enough
back,
is kind of
go
one
back.
of those things.
Is it low because you would have picked one already? Or is it low because you probably haven't gotten one yet?
Well, so let's do part C, and I think that'll help answer that question. Okay, so it's not particularly low. It's almost a 50% chance. Right, 0.446
I
is.
have 0.04.
Oh.
0.04.
It is 0.04.
Oh, it is 0.04?
Yes.
Sorry. That is pretty low. So that's less than a 5% chance.
Uh-huh.
All right, well, let's take a look at this, especially the first part. The mean number of men and the standard deviation we would expect to check before finding one that's colorblind. So the expected value of 8, or excuse me, the expected value, sorry, before finding one, my fault. It's the expected value. It's just going to be 1 over p. So that's 1 over 0.08. So that's, how many times does 8 go into 100?
15.
More than that.
16.
Less than that.
So 15.38.
And Ian, what is it?
12 and a half.
Oh. Killing me.
So the reason that that's so low is that this says you're going to have to pick 12 or 13 before you get the first one.
So
Getting
it's
one
low
in the,
because you haven't picked one yet.
pardon?
So it's low because you haven't picked one yet, not because you did before the 8th try.
Say again?
So the question is, what's the probability it's not till the 8th try that you pick someone that's colorblind?
Right.
The reason that the number is low is not because you would probably pick one before 8.
You probably wouldn't.
The reason it's low is because you probably wouldn't.
Right. Right. All right, and then the standard deviation, sigma, is going to be equal to the square root of p, which is 0.08, over 0.92 squared. Or you could just do the square root of 0.08 over 0.92 squared. And I got that that was 0.307. So let's think about it in those terms. So if the standard deviation is 0.3, just ignore the 0.7 for just a second. To get all the way down to 8 from 12 and a half, it's going to take more than 3 standard deviations just to move it down about 1. So this is way in that this is not very probable territory.
Take 14.6 standard deviations.
That's a lot of standard deviations.
Yeah.
All right. So let's take a look at this next one. So if there are 12 guys in your AP English class, and we know that one of them is colorblind,
Survive.
what is the probability that the 8th guy picked will be the one that is colorblind?
Probably close to 42.
You're going to be surprised.
5%.
So the probability, so the first guy you pick, do you want him to be colorblind or not?
No.
No. So what's the probability that the first guy that you pick out of the 12 is not colorblind?
Wait, 19. Wait.
How many colorblind guys are there?
1.
How many non-colorblind guys are there?
11.
11. So what's the probability you'll pick a non-colorblind guy?
11 out of 12.
11 out of 12.
Oh.
And then, God bless you, when you pick the next one, how many non-colorblind guys are there now? It's 10 out of 11.
Oh.
And then 9 out of 10, that's the third guy. Bless you. And then 8 out of 9, the fourth guy. 7 out of 8, that's the fifth guy. The sixth guy is 6 out of 7. Seventh guy is 5 out of 6. And then the eighth guy
1 out of 5.
is 4 out of 5.
Wait, what?
Don't you switch it because you want him to become
Yeah.
1 out of 5.
Oh, sorry. What does that equal to?
0.05.
Now look at all the things that cancel.
Oh, that's a lot.
Ooh. 1 over 12.
It's 1/12.
0.05.
So it doesn't
Oh
change.
gosh.
Think about that for just a second. If you lined all the guys up, and one of them is colorblind out of the 12, the probability of any of them being
What the heck?
colorblind is 1/12.
Alright.
Why would you do all that?
Because it's kind of fun to go, oh, that does work.
I'm still confused.
So if you lined up 12 people, right, and one of them is colorblind, what's the probability that the first one is colorblind?
1.8.
1/12, right?
Okay. Is that
What's the
same
probability that the fifth one is colorblind?
thing? The same.
It's the same.
But I thought you knew one of them was colorblind.
I do.
So then when you take one out, why doesn't it increase?
Because what happens is when you take one out that's not, then the next probability gets smaller, right? And you're multiplying all these probabilities together, and everything cancels except for the 1 and the 12.
Okay. Let's do.
And it makes sense, right? When you start, you're like, okay, what's the probability that, pick a guy that
Well,
he
like
happens,
when you have 2 left,
right?
it's 50.
Right. So I'm not talking about what's the probability that after having eliminated the first 10, what's the probability of the remaining 2.
Oh.
I'm talking about the probability from when you start that it's the 8th guy. Okay? All right. So, page 2. What if from our previous example we selected 8-minute random and we want to know the probability that exactly one of them was colorblind?
Is it not 0.8?
No, it is not 0.8.
What minus one?
We know exactly one of them's colorblind though, right? So here's how we're going to do that probability. The probability is going to be equal to, well, it could be the first man, it could be the second man, it could be the third man, it could be the fourth man, the fifth, the sixth, the seventh, the eighth, right? How many different possibilities is that?
8.
8. There's 8 different possibilities.
Wait, I thought there was 12 men.
Well, we selected 8.
Oh.
So now we've selected 8-minute random. And we want 7 of them to be colorblind,
Wait.
or not colorblind, excuse me.
I was like,
And we want the 8th one to be colorblind. I don't have the number for that one.
0.357.
0.357. So if you had a group of 8 guys, the probability that exactly one of them is going to be colorblind is about 35.7%.
wait, so that's high.
Yeah.
I'm so confused.
Why does that not make sense?
Just does.
Like, the probability that you grab like a red Skittle out of like 8 non-red Skittles is not 35%. Alright. It just doesn't make sense. Like, alright,
Wait,
so if you got like a red M&M and a
I
bag
see
of
what you're saying.
non-red
I know what you're
M&Ms,
saying.
yeah, and
Right.
like it's 1 out of 8. It's not a 35% chance that you're gonna grab the 1 out of the 8 that's red.
But it is.
No.
I'm just confused
All right,
on.
so we have 8 Skittles.
Yeah. One of
Right?
them's red. The rest aren't.
Well, that's not what this says.
We don't know that one
Oh, we don't know that one of them.
We don't know that one of them is colorblind.
But still.
Okay, but like the probability that 1 out of 100 of them are going to be colorblind is what? What do we say? Like
8 out of 100.
8%. So,
So 8 out of every 100, there's going to be one that's colorblind,
so
right?
if we lower that sample
Because it's
size,
out of 8 is why it changes, right?
like it doesn't have to make sense to me. I'll do the numbers. But it's
Yes, ma'am.
Sure.
You may.
I I get it now.
Lucky.
So we want to have a group that has 7 non-colorblind and 1 colorblind.
We
Right.
want that. So we know that that's there. How do
Yes,
get
we,
it
we want to have, right here it says we selected 7,
from our previous
8-minute random, and we wanted to know how many possible ways are there for exactly one of them. No more, no less.
All right, I like kind of see what you're saying.
Yes.
Like, the reason that it goes up is because if you're grabbing 1 Skittle out of 100, it's not a big chance. But if you're grabbing 8 Skittles, it's a higher chance
Yes.
that one of them is red.
Because you know one of them is right.
Because
Now,
you grab
we
more
don't know that one
Skittles
of them is red, but we now have a group of 8.
instead
Okay.
of 1.
I kind of see it.
So if you had a bag of Skittles where every 10th Skittle was red, right?
That's really good
And
explanation.
you picked 8 Skittles out, what's the probability that you have exactly 1? It's a pretty good probability.
All right.
Okay?
Thank you, I appreciate it.
All right. So this is getting into a different idea. What if we want to know the probability that 3 of the 8 men were colorblind? That gets a lot more difficult because you have to think of, well, what are all the different ways I could have 3 different men colorblind? It could be the first, second, and third. It could be the first, second, and fourth. It could be the first, second, and fifth. And you could go crazy trying to list all of those.
How many is it?
Factorials.
A good amount.
24.
It does use factorials, but fortunately, you're not going to actually have to because your calculator will do all this for you.
Yay.
It turns out that there are 56 different ways to do it.
Oh my gosh.
And I actually listed them all and was like, okay, let me think about all the different ways you could do this. And I listed them all and I'm like, okay, this is crazy. Okay? I did just because I wanted to make sure that I understood exactly what was going on.
Pre-calculator age, was this all done by
Just
hand?
for funsies?
Pardon?
Pre-calculator age, was this all done by hand?
Yes and no. They wouldn't have listed them all because there's a fast way to do it.
Oh.
It involves using factorials, but it's still way faster than trying to count all of them.
I just think it's so impressive that so much math was discovered before calculators.
Yeah, it is pretty amazing. So for this, we have what's called a binomial model. Okay, and this is how many successes? That's the question. You're not waiting until you get a success. It's, I have this group, how many successes? So here, n is still the number of, is going to be the number of trials. So with a geometric, you never know how many you're going to need until you get a success. Here, you've got this many trials. You get this many chances, how many are you going to get? The probability of success is still P, and Q is still the probability of failure, 1 minus P. Capital X is the number of successes in n trials. So in your Skittles deal, I've picked 10 out. How many times am I going to have a red out of those 10? Okay?
Yeah, okay.
That's the question you're trying to answer.
Yes, sir.
Okay? Here's the probability. The probability that x is equal to whatever that number is, you guys recognize this?
No.
This is
Yeah.
combinations.
Well, it's like the formula
For what?
for glucose.
Okay. This is n choose x. How many do you have and how many are you choosing? That is also sometimes written this way, n over x, and you'll see it this way on the AP exam, and I want you to recognize it. This is the same thing. It's just not the way your calculator writes it, and very few people write it that way. But this is the way they write it. Okay? Now, n choose x is n factorial over x factorial times n minus x factorial. You're going to use your calculator for this. You're not going to ever have to know this formula.
Yay.
Okay? The mean is n times p. So p is the probability that any one, multiply that times the number, that gives you the mean number that you're going to get. And the standard deviation, you will use this a fair bit, is the square root of npq. So let's look at an example. So according to a nationwide survey, I picked on the guys, so I had to find something to pick on women about. 6% of the women aged 30 to 39 in the United States are 5 foot tall or less.
Shorties.
We have randomly selected 8 women in the U.S. between ages 30 and 39. Can we use a Bernoulli trial?
Sure.
Why?
Because it's success or fail.
So there are,
Two.
We have to write this out every time?
when it says,
Just explain.
and actually you should write it out every time you use it before you use it. There are 2 possibilities.
Small and not small.
Tiny tall.
5 feet tall or less, and more than 5 feet tall.
5 feet.
What's the next stipulation?
The population
It's
is
the
less
same.
than 10%.
That's the third
It's
one.
the
P or
same,
Q.
but the probability is the same for everyone.
Right. So the probabilities don't change. Don't change with repeated trials.
So it's
It's always 6%.
Right. And we'll use a sample of less than 10% of the women aged 30 to 39 in the U.S. And I just use a lot of parroting when you're writing this. It says 6% of the women aged 30 to 39 in the U.S. I just write that all down. So yes. So now we want to find the mean and the standard deviation. The mean, what's the probability that so it's n times p. So there were 8 women, 0.06, 0.48. If you only pick 8, you only have about a 50-50 chance of picking one that's 5 foot tall or less. The standard deviation is a square root of NPQ, so it'll be 8 times 0.06 times 0.94, and that is 0.672.
Did you just do that in your head?
No, I
Oh.
had this written down.
Yeah.
Mm.
Not.
So now we want to know what's the probability that 3 of the women selected are 5 foot tall or less. It's going to be pretty small, right? So the probability that x equals 3 is going to be 8 choose 3. So that's going to be how many different ways could you get 3 women? Which 3 women? That sounded wrong, didn't it? How many different combinations? And I can't work my way out of it now. How many combinations of 3 women can you make out of it? Wait a minute. Anyway,
How many ways can you get through emergency?
times 0.06 to the third times 0.94 to the fifth. And that's 0.009.
So very, very small.
Yes, they're below 5. Yes, there's a less than 1% chance that you could get free out of this. And I mean, there's only a 50-50 chance that you're going to even get 1. So that makes sense that it's going to go down pretty quickly. Yeah, let's quit there since we don't have enough time to do the next part.
Calculator.
It's really bad math.
One thing I'll point out real quickly is that